Today I'm gonna start off with a quick introduction to Mach modular forms and harmonic Maass forms. I'll briefly introduce a little bit of the history and then go into some of the aspects of Mach modular forms, Maass-Poincare series that are important for the theorems that I've talked about yesterday and we'll talk about tomorrow about moonshine and Umbral Moonshine. So, Mach modular. Okay, so in 1920, Ramanujan sent his last letter to Harvey. And in that letter, the letter contained 17 mysterious functions that he called Mach theta functions. Okay, that he had recently started looking at. And the way that he described these functions, he was looking at functions that somehow look like classical theta functions, but we're not. Okay, so a quick example of this would be, so he gave a function f of q, which is given by 1 plus summation of n greater than or equal to 1, q to the n squared over 1 plus q, 1 plus q squared, dot, 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 1 plus q to the n, all of these squared. Okay. And this somehow is very similar to a particular form for the partition function. So the partition function, so 1 over eta of tau, and then I'll just briefly normalize this to get rid of the fractional power of q there. This can be written as 1 plus the sum n greater than or equal to 1 q to the n squared over 1 minus q squared, 1 minus q squared, quantity squared, 1 minus q to the n squared. Okay. So somehow this function it kind of had the same general shape, as this other modular form, but it was not a modular form. Everything that he wrote in that letter was a little bit, it was very vague. It was a little bit vague about what exactly he meant by looks like a modular form. And so these functions remained very mysterious for a very long time. Many people have studied them. There's several linear relations among the Mach theta functions that give honest modular forms. Okay, so they were known to somehow be related more than just this vague looks like a modular form. They somehow did fit somewhere into this theory, but they were left, how they fit precisely was left very open for quite a while. Let's skip ahead a few years to 1949. Okay, so Maass was, he defined what he called a Maass waveform. Okay, and so Maass waveform, there's, well, it's a function that's modular for some group. So f of a tau plus b over c tau plus d should equal c tau plus d to the k times f of tau for some weight k. Okay, so it looks like a modular form. There's some differences of the definition here. Sometimes this is normalized a little bit differently by multiplying by a power of y so that this factor of automorphies has absolute value 1, but we'll just use this definition for now. Let's see. For all matrices A, B, C, D inside some group gamma. And maybe sometimes also we'll throw in a multiplier system here. That's fine. Anyway, basically it looks like a modular form, but instead of being holomorphic, we're going to relax that condition, and we're going to say that it's an eigenfunction for the hyperbolic Laplacian. Here, delta sub k is equal to minus y squared delta squared over delta of x squared plus, partial squared over partial of y squared plus I ky partial over partial x plus. Yeah. Okay. Okay. Great. And here, tau is equal to x plus I y. Great. Okay. So it should just be an eigenfunction for the Laplacian. If s is equal to 0, we call this harmonic. And notice that this includes classical holomorphic or weakly holomorphic modular forms. Okay. Great. Usually also, well, we also have some growth condition. At cusps.
Are you specifying what gamma is?
Right now, no. We'll say that it's a Maass waveform for some group gamma. For this purposes, it's going to be some congruent subgroup, or something similar to what we looked at yesterday for the moonshine groups. But yeah, just some subgroup of SL2Z or SL2R.
For the growth condition, there's a standard choice?
Yeah, so his original choice was that it should be at most polynomial growth. At most polynomial growth of the cusps as y goes to infinity. For a Maass cusp form, it should vanish as you go to the cusps. For our conditions, we're going to actually allow singularities at the cusps, but we'll talk about that in a minute. Okay. But yeah, similar growth conditions to standard modular forms.
So here, harmonic means
Harmonic means, yeah, it means that it's in the kernel of the Laplacian.
but it is ky, right? In general, harmonic means there is no that part, right?
So this is kind of So there's a way to adjust this function. So if we multiply by a specific power of y, then we can change this function so that this factor of automorphy will always be absolute value 1. Or absolute value 1. And in that case, you'd adjust your hyperbolic Laplacian in a similar way, and you end up losing this term. Okay, so then you're always looking at just the standard Laplacian. Okay, and so then a harmonic comes to mean the same thing in the traditional sense.
Complex number or S can be complex number?
Yeah, it can be. Again, it certainly can be. We're going to primarily be interested in harmonic Maass forms here, but yes, yeah, it can be complex. Well, I guess, yeah, we will be talking about Maass-Poincare series in a minute that will, where S can be various values. Okay.
What can K be?
So usually K is an integer. It depends on how you define some things. For our purposes, we'll say half integer. Yeah. If it's not an even integer, then you have to have some multiplier system in order to make things consistent. But yeah. So yeah, we'll allow half integer weight with multiplier system. Okay. Great. Okay. So let's talk about some examples of harmonic Maass forms. Okay, so So this theory, this was mostly studied for not harmonic Maass forms. So Maass-Cus forms has a very rich theory here. When you're looking at harmonic Maass forms, well, for a long time, there weren't very many explicit examples that people could actually write down. So there was, we do have one nice example. So this is the extended Eisenstein series E2. So you have the standard 24 plus the sum of n qn over 1 minus q to the n. Okay, so this is the standard Eisenstein series E2, which is not quite modular. And then if you subtract 3 over pi y, this now becomes modular, and it satisfies the condition to be a harmonic Maass form. In 75, Zagier produced another example. This is a generating function for the Hurwitz-Kronecker class numbers. So n equals 0 to infinity of h of n q to the n plus 1 over 16 pi y sum of over integers m beta of 4 pi m squared y q to the minus m squared, where beta is equal to beta of t is equal to this integral here. Okay. So yeah, so that was in 1975. Zagier proved that one. And
What is H?
so Hn, these are the Hurwitz-Kronecker class numbers. So the standard class numbers weighted by the order of the automorphism group. Okay, and then also h of 0 is equal to minus 1/12. Okay. Great. Okay. So other than that, there really weren't very many concrete examples of harmonic Maass forms that we could actually hand to you, or that we knew were harmonic Maass forms, until Zweigers this was work in the early 2000s. Papers were published in 2001 and 2002. So in Zweigers' thesis, what he showed was that each of Ramanujan's Mach theta functions can be completed to become a harmonic Maass form. Okay, so given, for instance, the example that I showed earlier, the f of q, okay, there is some non-holomorphic function. Let me call this n of q, and then I need to multiply this by q to the minus 1/24, okay, whatever, so that this function here is a harmonic Maass form. Okay, and you show that you could do this for every one of Ramanujan's Mach theta functions. Okay, so now suddenly that whole list of functions, they made sense. They, where they fit into this theory of modular forms. It made sense why linear combinations of the Mach theta functions would give you modular forms. You were looking at linear combinations that would annihilate the non-holomorphic part. Okay, and then it also gave us a large list of examples of, or concrete examples of harmonic Maass forms to look at.
What are some properties of this non-holomorphic part?
So, well, let me get to there in just a moment. There's a differential operator that I'll get to in just a moment that shows that this non-holomorphic part, it'll send this non-holomorphic part to a holomorphic modular form of positive weight. Okay. So, yeah, more than that. Well, that's exactly where I'm coming right now. So, Brunier and Funke wrote this paper on two geometric theta lifts, where they, and in this paper they outlined a lot of the properties, investigated a lot of the properties of harmonic Maass forms. They fleshed out this a lot of this theory in there. So let's. So the first thing is that we have this fundamental lemma, which goes like this. So first of all, we have this this differential equation that says, for a harmonic Maass form, I'm saying that the image under the Laplacian is 0. This gives a differential equation that has two solutions. So we can split a harmonic Maass form into two pieces. Okay, so if I have a harmonic Maass form m of tau, I can write this as a sum a plus of n q to the n plus a minus of 0 y to the 1 minus k plus a sum let me just write that in there for the moment. A minus of n gamma of 1 minus k absolute value of 4 pi n y q to the minus n. Okay, so you've got a holomorphic part that looks like a Q series. Okay, depending on how we define our growth condition, we can have kind of a non-holomorphic constant term here, and then we have this non-holomorphic part here. Okay, so you'll have a coefficient here, and then right here is an incomplete gamma function. Sorry, that's not a minus. Okay. So the upper incomplete gamma function times the power of q. Now, this looks like, because I've got a q to the n with n less than 0, this looks like I've got a massive singularity due to the growth conditions for gamma. I could actually write this instead as a sum over n positive minus bar of n tilde 1 minus k 4 pi ny times q bar raised to the n. Okay, so I can rewrite this as a function here, which is bounded polynomially in y. So this is bounded by y to the 1 minus k, this piece here, and then I've just got a power of the conjugate of q here. Okay, so you can see that the way that I've got this written here, there's no singularity here. Again, you can relax some of the growth conditions to allow singularities. You end up having to use a analytic continuation of the incomplete gamma function. Okay, but it still works. For our purposes here, let's just let n be greater than 0.
What's the gamma function of?
This is the incomplete gamma function. So gamma of Sx is going to be the integral from x to infinity of, let's see, t to the s minus 1 e to the tx dt. I think that's right. What's that?
Minus t.
A minus t up there?
No way. 36. In general, the gamma function minus t plus minus t dt.
Minus t dt.
To the power minus t dt derivative. Original gamma function.
That right there. Oh, yes. Yeah. Sorry. Yes. Apologize for that. Yes. But that's, yeah. So it looks like the gamma function, but instead of integrating from 0 to infinity, it's from x to 0, or x to infinity. Yeah. And this has an analytic continuation. But yeah. Okay. Anyway. So this is what our non-holomorphic part looks like. Our holomorphic part looks like this. Okay, so we'll often refer to this part as the holomorphic part. Or, for historical reasons, going back to Ramanujan, the Mach modular form. And then this part called the non-holomorphic part. Okay, so we usually denote this by H plus and H minus. Okay. So In the theory of Maass forms, so this is back before Brunier and Poincare certainly, there's this differential operator, xi sub k, which is defined to equal 2i y to the k partial over partial tau bar. Okay, so take a partial derivative with respect to the conjugate of tau, and then conjugate that whole result, and then multiply by 2i y to the k. Okay, so this has several nice properties. So if I use it twice, so, well, I guess the first thing that I should say is that this preserves modularity. But it sends weight k to weight 2 minus k. So a harmonic Maass form, or a Maass form of weight k, will be sent to a Maass form of weight 2 minus k. It also has this very nice property. If I do this twice, so use ck and c2 minus k, this is just the same thing as the hyperbolic Laplacian. So that means then that it will preserve the eigenvalue with respect to the Laplacian as it changes the function from weight k to weight 2 minus k. Okay, so yeah, so weight 2 minus k is dual to weight k. Yeah, dual. Yeah. So as an operator, so if I send xi of weight for 2 minus k, if I act on a harmonic Maass form, weight 2 minus k, this is going to annihilate the holomorphic part. Sorry. What I'm about to say is only true for a harmonic Maass form, but it will annihilate the holomorphic part, so it's the same as just acting on the non-holomorphic part. Okay, and the result is this will be a holomorphic modular form. So n greater than or equal to 0, 4 pi n to the 1 minus k, a minus of minus n bar q to the n. Okay, so conjugate of that. Okay, so this will give a holomorphic modular form. And if we tweak the growth conditions so that this part, so that there's no a 0 here, we'll actually end up with a cusp form. Okay. MK of gamma for the same group. Okay.
Here, large H is harmonic.
So my large H is a harmonic Maass form. Okay, so I'm using M over here and H over here. Yeah, let me change this to M. Yeah, okay. So if I act on it on a specific harmonic Maass form with that shape, then I'll end up getting a modular form like this.
So is this a weight 2 minus k? Okay.
This is now I said k over there, yes? Okay, then let me change this to weight k. This is weight 2 minus k. So usually what you're looking at here is the harmonic Maass form is something of negative weight, and C will send it to something of positive weight. So that's why right here I wanted to act on it. I wanted to have M of weight 2 minus K and send it to positive weight K. But yeah, for consistency, I'll change that for you. Yeah, so if I make the holomorphic part equal 0, then, well, so that's going to act, see, I've got a y to the 1 minus k here. Yeah, so the holomorphic part will, the holomorphic part will vanish. If I make that constant term 0, then that's just n greater than 0. Yeah, it just acts on the non-holomorphic part. If I make that constant term vanish, n greater than 0, so then this will become a cuss form. Great. Okay. Great. In the case of Zweig's theorem, okay, the non-holomorphic parts, the shadows here, I haven't defined that. Okay, this cuss form here is referred to as the shadow of the non-holomorphic, or the shadow of the Mach modular form. Okay, so the cuss form that you get by acting on our harmonic Maass form by Xi is the shadow of the Mach modular form. Sometimes we'll say shadow of the harmonic Maass form, but Zagier doesn't like that terminology. He invented it, and so we'll go with his wording here. So it's the shadow of the Mach modular form. Okay. So does that answer your question about the non-holomorphic part? Is there anything else about that you wanted to? Okay. Great. Okay. So I guess one point that I'd like to make here, if we pick gamma so that this space of cuss forms is 0, so for instance, when gamma is a genus 0 subgroup, then in that case, all of the harmonic Maass forms with the growth condition that we've described here all have to be weakly holomorphic modular forms. Okay? Because that means that the image under Xi has to be 0, which means this non-holomorphic part has to be identically 0. Okay. So the next thing I wanted to talk about is the Maass-Poincare series. So this is a way of creating a basis for a space of harmonic Maass forms. Okay. Yeah.
Here, H minus is 2 parts here, and for H minus.
Yes.
So 2 parts.
Yeah. So H minus. Sorry, I'm using H's and M's. Okay, let me change these to M's. Yeah. So it will include this piece, but from this point on, let's just assume that this piece is 0. No. This is an alternate expression. Yes. Sorry. Yeah. Sorry about that. Okay. So the Maass-Poincare series. So this gives us a way to create a basis for a space of harmonic Maass forms. So the classical Poincare series, let me describe these really quick. So if I have weight, so positive even weight, k greater than 2, and an integer.
You assume k is frequently larger than 2 and k is even integer?
Yes. Yeah. So k is an even integer strictly larger than 2, and then n is any integer here. I can define a Poincare series. Let me call this pk of n, and I'm going to define this to be an average of an exponential function zeta plus d to the k. Okay, and then I'm going to make the sum over all matrices A, B, C, D in my group gamma that I want to work with, but then I can mod out on the left by the set of translations. So I'll call those gamma infinity. Okay, the stabilizer here. So this summation is basically forcing this function to be modular. Okay? As long as k is large enough, this converges absolutely. Okay? Great. So these are the standard positive weight Poincare series, and they create a basis for a space of weakly holomorphic modular forms. If n is positive, this will be a Cuss form, and creates a basis for the space of Cuss forms, and so on. This doesn't work for k less than, well, it doesn't work for k less than 2, certainly not for k negative. And so we want to modify this construction a little bit to get something that will work in the negative weight case. The way that we're going to do this, we're going to use, instead of the exponential function here, which is holomorphic, we're going to use a non-holomorphic function, which will the shrinks fast enough that the averaging will converge absolutely. So the way that we're going to do this, we're going to use a Whittaker function. So in this case, let me set k less than 0. We're going to avoid the cases in between 0 and 2 for the moment. And then let's define a function phi sub ms of tau, which is going to equal e to the mx. This here is the M Whittaker function. K halves sine of m s minus 1/2. Okay, so the indexes for the Whittaker function, the argument will be absolute value of 4 pi my, and then we'll weight this by 4 pi y to the minus k halves. Okay. So this function, the reason that we want to use this function is, first of all, it's an eigenfunction for the Laplacian. Okay. The eigenvalue is s times 1 minus s minus k times 2 minus k over 4. Okay. So that's nice. It also decays fairly rapidly. So phi of ms of tau is equal to big O of y to the real part of s minus k halves as y goes to 0. And this part is what we need so that this averaging will converge absolutely. Great. Okay. Now, if we want to get a harmonic Maass form out of this averaging procedure, we want to specify S to be, either k or either k halves or 1 minus k halves. Okay. Since k is negative, we're going to take S to be 1 minus k halves. And in that case, so if S is equal to 1 minus k halves, this will be harmonic. And then what we end up getting is that phi is equal to 1 minus k, gamma of 1 minus k times q to the m minus 1 minus k incomplete gamma function 4 pi my q to the minus m. Okay. So, so if we take m to be negative, we'll get something with a simple pole here, and then this will, and then there won't be any pole there. Okay, so we're choosing a function here that has a specified, it has the pole of any particular order that we want, and then a non-holomorphic part here chosen specifically so that we end up getting this rate of decay.
The pi ms. Your pi is pi ms.
Where are we at?
The rest line.
Last line.
This one?
No.
Left side.
What is pi?
Yes. Yes.
So what is the
What's that?
what's the first line? M.
This m minus k halves times the sine of m, and then s minus 1 half. So m mu v is the standard M. Whittaker function. Yeah. Okay. Great. Okay. So now, in this case, so we have, again, k less than 0, m less than 0. Let's define this Poincare series. I'll use a Q this time. Q, K, M. And let me leave the S in here for the moment. And this is going to be this averaging of phi of M S. I don't need the M there. A tau plus B over C tau plus D. C tau plus D to the K. Okay. And this will converge absolutely. It also has a very nice property that if we act on it with Xi, this is equal to minus is equal to K minus 1 times 4 pi m to the 1 minus yeah, that's right. Okay, to the 1 minus k times this other Poincare series, pk m. pkm. And I'm sorry, this is when I'm specified at s equals 1 minus k halves. Yeah. So the harmonic Maass form, the shadow, is given by this holomorphic Poincare series. Okay. Now, since we can create a Poincare series like this with any order of a pole that we want,
P2 minus P.
yes, thank you. Yes. Yeah, the dual weight. Great. Okay. Now, since we can choose m as any negative integer, we can create a harmonic Maass form with any order of a pole that we like, and so this can create a basis for the space.
In right hand side,
Yes?
in elastic, m is maybe minus m.
Yes, you are correct. Yeah. So here, if m is negative, then we will get a Poincare series with m positive, which will be a cusp form. Yeah. Perhaps I should have written this different with my signs, but yeah. Great. Okay. Another point here that's worth noting, again, if I choose my group that I'm averaging over gamma so that the space of cusp forms is 0, okay, so a genus 0 subgroup, then what that means is that my Poincare series has to be weakly holomorphic. Okay? And so this is what happens in the case of Monstrous Moonshine. Each of the groups involved in Monstrous Moonshine are gamma 0 or are genus 0 subgroups, and so we can create a Poincare series of this form, and the Poincare series will be weakly holomorphic. Okay, so it will end up having to be the Haupt module in Monstrous Moonshine, assuming that we pick m to be 1. Minus 1. Yeah. Okay.
So here Q is the shadow of some Q.
P is the shadow. Q is the Maass form.
P is the shadow.
Yeah. Yeah. So Q is my Maass Poincare series. The shadow will be the cusp form P, which is a holomorphic modular form, a holomorphic cusp form.
I think you should TK send the shadow to the cusp form.
So the shadow is the cusp form. So this will send the non-holomorphic part of Q to P. Yes, that's true. Yeah.
Then what is the holomorphic part of Q?
The holomorphic part of Q, well, it's annihilated by this. It's a Q series, but I'll give you the expansion for this right now. Let's see. One point that I'll say here. So this only converges. Okay, because of my decay rate here, this doesn't quite converge for k equals 0. Well, I can set k equals 0, but s it won't converge at s equals 1. But I can take the limit as s goes to 1. So that will give a Poincare series for weight 0. Maass Poincare series for weight 0. Okay. So the reason this is useful is because this gives us.
This can apply to the things appearing in the Monstrous Moonshine,
Yes.
but don't they have k equals 0?
Yes. So that was a point that I just mentioned but brushed over a little bit. So I can do this averaging at k equals 0. The averaging is fine, but I have to take it only converges for real part of s bigger than 1. So how I get around that problem is I take the limit as s approaches 1 along the real axis, and it does actually converge then. Yeah. Great. So that'll be a little bit more clear, I think, when I write out the formulas for the coefficients. You can actually see that at that point it's easy to see what that you can stick in s equals 1. So this QKMS, okay, I can write this as, so doing this averaging, I have the part that comes from the identity, so that's just going to be the original phi ms. Okay, and then I'm going to have this sum. Let's see. Sum. I'll have the holomorphic part here, a plus q to the n, plus the non-holomorphic part. So I'll have a minus of n. The incomplete gamma part. So it'll be 1 minus k 4 pi my q to the minus n. Okay. So it'll have an expansion like this. And the way that we're going to extract the formulas for these coefficients is as follows. So the summation is over matrices in. So I'll have my group gamma, and then I'll mod out on the left by the translations. So what this is going to look like, if I have a matrix A, B, C, D, okay, I should be able to pick. So what I'll have here is I'll have the identity element, and then besides the identity element, I can take C greater than 0. And then because I'm modding out on the left by translations, I can take, let me do it this way. C greater than 0. I can take A to P between 0 and C. Okay. Then I'm going to take D. I can write this as maybe a big D plus M times C. Okay, where big D is, again, between 0 and C. Okay, so this summation over this group here, I can end up writing this as a summation over C bigger than 0, summation A times D. So A and D should be inverses mod C. Okay. And then I end up having a summation over, sorry, I'm misusing that letter M. Let's just write this N. Okay. And then I can sum over N in the set of integers. Okay. Now using this part, I can do Poisson summation, and that will allow me to extract these Fourier coefficients.
So you mean this sum plus the one term that corresponds to identity?
Yes, that's correct. Yes. Okay. So again, yeah, so the identity is going to come out to this. This part in here, I can do the Poisson summation, and that's going to give me these coefficients here. Okay. So what this is going to look like, so the way that I have these well, okay, so let me just write A of n. The formula is actually going to work out the same for these, but if n is positive, then I'm looking at A plus of n. If n is negative, I'm looking at A minus of n here. Okay, so this formula is going to be given by 2 pi I to the minus k over, gamma of 2s over gamma of s. Oh, I got that wrong. Let me do it this way. Okay, so a plus or minus up there. I'll have a plus or minus right here. So the k halves, absolute value of n over m to the k minus 1 over 2. Summation, c greater than 0. Here I'll have a Kloosterman sum. And then here I will have a Bessel function. In just a moment, I'll write which Bessel function. The argument will be 4 pi square root of absolute value of mn. Sorry, that's very hard to read. Over c. And then the Bessel function that I'm looking at, b plus, will be is the I Bessel function. B minus will be the J Bessel function. The index here is 2s minus 1. Great. Okay. So it's a little bit nasty to look at. This sum over C is going to be this same summation over C. The summation here for integers a and d, whose product is 1 mod C, is going to be swallowed up into the Kloosterman sum. Okay. And then the Poisson summation is going to give us the Bessel function. Okay? That Poisson summation involves kind of a nasty integral to evaluate, but it's the same integral every time. It's already worked out in, well, at least the value is given in several papers, so that's mostly just a lookup. If you change the group that you're looking at, if you throw in a multiplier system or something like that, all of that tends to modify the Kloosterman sum. Sorry, give the Kloosterman sum kind of a little bit of a different shape, kind of a modified Kloosterman sum. But basically, all of the Maass-Poincare series will have the same basic shape. Okay, and then in the case of the Monstrous Moonshine that we were looking at yesterday, of course, k will be 0, and we'll simply evaluate this at s as s goes to 1. Okay. Great. Okay. So it's 4 o'clock, but at least let me just quickly say something really quick about how to go from there to weight 1/2. So tomorrow I'll be talking about Umbral Moonshine, and that will be, we'll need the weight 1/2 Maass-Poincare series. In that case, okay, again, we can take k equal to 1/2 without any problem. The question is whether the series converges when we take s equals to 3/4 or not. Okay, and that's the question. This has been shown to converge in many important cases. the same technique basically applies anytime we want to modify it. Basically what happens is you'll have this term. The first few terms, for low values of C, everything's going to be dominated, of course, by the I-Bessel function. But once C is large enough, this will be bounded. And then the question becomes whether the infinite sum here will converge or not. So we begin, this comes down to this question about the Selberg-Kloosterman zeta function, which is given by the sum over C greater than 0 over C. Okay. The question is, does this converge? This is 2s, I think. Yeah. Minus. Yeah. Okay. So then the question becomes, you can bound the terms the expansion here in terms of the Selberg-Kloosterman zeta function, and the question becomes, does this converge at s equals 3/4? This was shown to converge by, so Sarnak showed that this converges at s equals 3/4. There's a method due to Hooley that's maybe a little bit easier to give actual bounds, explicit bounds. But one way that you do this is you can rewrite this in a couple of steps to write this as a Salier sum, write that as a sum over CM points. Sum of a function over CM points, and then the equidistribution of the CM points can be used to give you convergence, and in particular it can give bounds. The bounds that this gives you are generally pretty nasty, especially compared to the size of the coefficients that you end up usually computing. So it usually gives a very large bound, but then it grows much slower than the main term, which occurs here when C is at a minimum. Okay. So yeah, let me stop there, and thank you.